Hello everybody, this is the basic models video in the large-scale machine learning section of ML Expert. In the previous videos, we talked about how using HDFS and a Spark cluster in conjunction can help us create our features and labels. Now that we have our features and labels, in order to explore different models, we need to train models. As well as just for exploration, let's say we want to eventually experiment with the model and potentially even launch that model, we'll eventually have to automate some sort of training such that the model stays up to date with all of the most recent features. We'll talk more about this automation later, but for now, at least for exploration, let's figure out how to train some basic models. Now, in the machine learning crash course section, we went over several different models, but usually those models were designed for a single processor and maybe not so large of a dataset. The idea of this video is to go over algorithms we can use for large datasets and how some of those algorithms might have to be altered or parallelized in order to make them work most effectively in a large data setting. First up, let's talk about gradient boosted trees. Again, we reviewed this model in the machine learning crash course, but we'll go over it briefly now. If you need any more context, feel free to revisit the decision tree video. So let's say that we have 100 million examples. Each of the examples has 200 features, and roughly there's about 200 split points per feature. Now, to refresh our memory on what this algorithm would mean for data these sizes, we can go ahead and look at a quick example. So here, for each feature in each of these feature vectors, we're going to evaluate some particular split point, and we're going to store the best split point across all possible split points, and then that split point will be assigned to be officially the node's split point. Then we will recurse to the left, and then we will recurse to the right, repeating the same exact algorithm that we already did for the parent node. The problem with this is we're not taking advantage of anything that we can do in parallel. So some pretty obvious things that we can do is analyze every single feature and every single split point for every single feature in parallel. A less intuitive thing that we can do is analyze every single node on a particular level in parallel as well. So here, that would mean evaluating all the features and the split points of each feature for every single node as we descend down the tree. Finally, one of the major portions of the gradient boosted tree algorithm is to sort the features in order to find their split points. By simply using the originally sorted split point feature list in a clever way, we can prevent ourselves from needing to resort every time we want to evaluate a particular split point. And finally, for gradient boosted trees, we can't parallelize the ensemble technique that is boosting because the subsequent tree depends on the previous tree. Now, with random forests, we can actually parallelize the construction of each tree in the ensemble because there is no dependency. Now, in general, all of these parallelized operations that we've talked about can speed up the training of gradient boosted trees and random forests upwards of 90%. Next up, let's talk about matrix factorization. Now, if you recall, in the machine learning crash course, we said that matrix factorization can use alternating least squares. It uses alternating least squares to approximate some user product matrix or user item matrix, such that two embedding matrices, so here a user embedding matrix and a product embedding matrix, when multiplied together, will approximate the original user product matrix. How it works is by alternating the optimization of the user embedding and the product embedding. As it alternates, it performs ordinary least squares. Let's say we have 100,000 products and 100 million users. These embeddings can get quite large. So we can actually split these embeddings up when we're solving for the alternate embedding. So here, if we're performing ordinary least squares on P while locking in the value of U, then we can multiply different sections of U across P such that we can still follow alternating least squares exactly while splitting it up across multiple machines. Now, as these machines calculate partial results, they will communicate with each other to make sure that all of the machines have all of the total results. Finally, let's look at logistic regression. This is the equation for logistic regression. If you need to refresh exactly what logistic regression is, feel free to watch the machine learning crash course video on logistic regression. Effectively, though, we've only went over how to perform logistic regression in terms of a single machine. If we have multiple machines available, then we would be able to put the parameters or the coefficients of logistic regression across the cluster. And then what we can do is send different data within a mini batch to each machine, such that this machine could calculate part of a mini batch, and this machine could calculate part of a mini batch. And they'll do that by executing the model of logistic regression. Each machine will get the partial mini batch gradient. They can ship the partial mini batch gradients back to some single machine here. This single machine will aggregate the partial mini batch gradients, adding them up. And by the way, typically we're not just going to use gradient descent for logistic regression. Most production-ready applications will use limited memory Broyden-Fletcher-Goldfarb-Shano algorithm, and effectively it's a variation of gradient descent, except they don't just use the gradient, they also incorporate the gradient of the gradient so that we can get more information about how we should update the coefficients of the logistic regression model. So what we're getting at here is that there's generally going to be some use or benefit of parallelization to these basic machine learning models. By basic here, I mean anything but deep learning. So these parallelization techniques often result in a faster convergence to the optimal parameter values. This means that we can train for less time and potentially have better models for the same amount of time. So how important is this actually? Well, let's say that we have a stock prediction model, and we incorporate all of the stock prices of all of the stocks throughout the last 20 years. If our model takes 3 days to train, and we're trying to make stock predictions about the following day, then we will never be able to use our model. So in some cases, limiting the training of a machine learning algorithm to just a single machine can completely eliminate the benefit of using machine learning. So fortunately for us, Spark has a library called MLlib, which implements parallelized versions and optimized versions of many of the basic models which we've covered in the machine learning crash course. Some examples include linear and logistic regression, SVMs, gradient boosted trees and random forests, naive Bayes, collaborative filtering, bisecting k-means, and singular value decomposition or principal component analysis. Notice here that k-nearest neighbors isn't implemented, so you'll typically want to choose another supervised learning algorithm, but there are implementations of k-nearest neighbors on a Spark cluster outside of MLlib. Now, beyond just the models, Spark also offers ways to analyze the performance of each of these models. So for instance, logistic regression, you'll be able to look at and tune the thresholds. As well, you'll even be able to find things such as the area under the receiving operator characteristic curve. In addition to all of these modeling capabilities and model analysis capabilities, MLlib also offers a series of data standardization and transformation techniques. So for instance, featured standardization, TF-IDF, feature hashing, stop word removal, one-hot encoding, and many more that I haven't listed here. Let's go ahead and see a demo of how we can apply Spark MLlib's version of logistic regression to our use case in which we want to predict whether or not users of our website, based on their website interactions, will cancel within a week or not. Alright, so let's train a simple model with Spark MLlib. This line here just uses Spark to read a Parquet file in the HDFS directory cancellation features labels. Now, this is a Parquet file that I've created, and if we read in this Parquet file and we show it, we can see that we have our interaction features, which we showed earlier in the series, and we also have our canceled within a week label. Now, this user here had 41 total interactions with the website over the past month. These total interactions include the number of searches or the number of clicks in a carousel that we would have on the home page. This user also had 9 interactions over the week and 0 interactions over the past day. Now, within a week of this last day interaction count, they did end up canceling their subscription. Now, this format continues for all the other users. Now, the first thing that we should do is isolate our features from the labels. So we do that with a vector assembler here. The vector assembler takes the input columns and has an output column. So here, our assembler is going to take the month interaction, week interaction, and day interaction counts and assign them to be a column called features. So if we take this assembler and transform our data frame to the assembler, then we end up with this here. Our users' features are 4190, and now we have a column dedicated to those same exact features. As well, we can have the same thing happen with the label. So here we're taking the canceled within week column, which is this one, and we're creating an identical column with the name label. So here we have user ID, features, and label. All right, now we want to actually begin creating our model. So how we can do that is by importing logistic regression from PySpark's classification library. Now, this cache operation makes sure that our data is available in the memory of all of the Spark nodes. If our Spark cluster isn't big enough to have all of the data in memory, some of the data will spill over to the disk. This cache operation ensures that we at least attempt to get everything into memory. So then we want to split our data into a training set and a test set. So here we can call dataframe.randomSplit. Now this actually uses a sampling library. So even if you put 6040 here, you could observe some variation from that exact number. Next up, we're going to define our logistic regression object here. There are many parameters that we can assign here, such as how much L1 or L2 regularization do we want, or do we want a combination of both? And we can also define here the max iterations that we want our algorithm to do when learning. But for now, we're going to leave most of the things to default and just set the max iterations to 10. Next up, we want to take our logistic regression object here and fit our training data to it. This fit is equivalent to training. Now that we have trained our model on our training data, let's get the predictions of our model from the test set. So here we'll call LR model, which is logistic regression model, .transform on the test data. If we show what the predictions produce, we'll get the identical data frame that we had above in our test set. So we'll get the user ID, the month, week, and day interactions, as well as the cancel within a week. Remember, we also added the features and labels to this. Now, the logistic regression transform method added a raw prediction, probability, and prediction column to this. So here, if we look at the prediction column, this user ID got predicted this value. Same with this user ID and this user ID. We see that we got predicted a 1, which is correct, a 0, which is correct, and a 1, which was incorrect. So far, with simply 10 training iterations, our logistic regression model got an accuracy of 66%. Now again, we would typically use far more data, and we would also have far more iterations, and also complete hyperparameter tuning. But this is just a high-level example of how you can use Spark to create basic models. That wraps up the basic models video in the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.